Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with strength of acids and bases, and we'll be talking about strong acids versus weak acids, strong bases versus weak bases, complete and partial ionization of bases and acids, and we'll be introducing acid-base neutralization equation. Acids are molecular compounds and are therefore formed by covalent bonds. Normally, molecular compounds do not ionize when dissolved in water, but if a certain bond within a molecule is highly polar, it is possible that a molecule may ionize when it dissolves in water. So we're looking now at strong acids and bond polarity. As can be recalled from previous lessons, whether or not a covalent bond is polar depends solely on the electronegativity difference between the two bonded atoms. Now we're showing you two molecules here. We have done this already when we did bonding. Nothing is wrong to repeat this. Here we're showing you the electronegativity values of the two bonded atoms in hydrogen. There's no difference between them, and same thing for chlorine here because they are homonuclear molecules. Now here these diagrams are showing you how there's even distribution of electron cloud between these two atoms. Same thing here, and that's why they are non-polar. However, now see what happens there. When you bond hydrogen and chlorine to form hydrogen chloride molecule, as you can see here, there is a big difference in electronegativity values between the two bonded atoms. There's 1.4 difference there. As such, this bond will be polar and the molecule also will be polar. The more electronegative atom pulls electron toward itself, so it acquires a small negative charge and it leaves the other end with a small positive charge. This figure here is trying to depict for you what happens in a single hydrogen atom. See, right now this nucleus is well neutralized by the electron cloud that's evenly arranged around it. If something happens where electron cloud is pulled towards the right, then this positive charge manifests itself as a small positive charge in that end because of the greater degree of electron cloud going that side, this side acquires a negative charge. If the electron cloud separates itself from the atom, then you're left with a nucleus all by itself here, and the electron goes over here, okay? Something similar is happening in the HCl molecule. We've spoken about this already, but we're just reviewing this because we're talking about why this guy will ionize. This is HCl. You can see chlorine is pulling a greater share of the electron cloud toward itself. As such, it acquires a small negative charge here, and it leaves that with a small positive charge here. Now, what can happen here is that if hydrogen chloride gas is dissolved in water, water allows it to ionize. So here's hydrogen chloride gas. It is neutral. If you pass that through water, it ionizes, and what is produced is called hydrochloric acid now. So here you've seen that chlorine is having 7 electrons, right, by itself. If it takes that one electron away that originally belonged to hydrogen, then the hydrogen becomes charged, becomes ionized, and the chlorine becomes ionized too. So hydrogen ion, and this is what we call a proton, okay? And this, of course, in your previous lesson, we said that this causes acidity, and that you have a chloride ion octet there. So this is why hydrogen chloride gas is neutral in dry air, but when you bubble it through water, it becomes hydrochloric acid. Note it is called hydrogen chloride here, and now it becomes hydrochloric acid there. You have to put in these little subscripts here to indicate the state of the gas. Inside it is in water now. So when it is in water, it's called hydrochloric acid. So this is how hydrogen chloride becomes an acid. When it is dissolved in water, the more electronegative chlorine atom takes the electron away from the hydrogen and ionization occurs. Arrhenius, if you can remember, found that acids such as HCl are very good conductors of electricity. So if they're good conductors of electricity, it means they must ionize completely in water, because we said that it is the ions in an electrolyte that are responsible for the conduction of electricity. So this is a little table showing you here the initial concentration of HCl, hydrochloric acid. That's initial. Initially, you don't have any of these, all right, because you didn't ionize it. Finally, as it ionizes, you won't have any HCl molecules remaining, because they all ionize to give you chloride ions and hydrogen ions. So this was the initial, and these are final concentrations of your chloride and ionized. It's like having, let's say you have 100 pairs of magnetic marbles, where you have white marbles are bonded to red marbles. Initially, you have 100 pairs, but if you separate them, you're going to have 100 white marbles separate and 100 red marbles separate. So there's complete ionization. When there's complete ionization or complete reaction, you notice that we put an arrow going like that, okay? You'll see a double arrow coming sooner or later when there's incomplete ionization. Arrhenius also observed solutions of some acids, such as ethanoic acid, or you call vinegar, and formic acid, and so on, conduct electricity poorly. He theorized for poor conductivity, there must only be few ions present in these solutions. This is what will happen if the acid only partially ionized. These acids, if they only partially ionized. And because they're only partially ionized, they're said to be weak. Why? Because they're not producing a large concentration of H plus ions. And this table here is trying to show you what is happening again. This is ethanoic acid. Okay, and we pointed out to you already that that is the ionizable hydrogen there. These are bonded to the carbon. They can be ionized, but because this bond here is polar, this OH bond is polar, this can break away and form H plus ion. So initially we have all molecules here, and of course you wouldn't expect to have any of these. But as it ionizes, look what happens. You have that number of moles per liter remaining compared to these. Huh? So there's poor ionization. So look, this is the initial concentration. Now you still have lots of these here. You have all of that remaining, all of that remains, okay? But we only have small concentrations of hydrogen and ethanoic ions. That's why you're going to see this sign here. This sign here means that the reaction is reversible. So how can we put that in perspective? Another way of putting that is say that this acid is only 1.3% ionized. In other words, if we have 1,000 molecules of ethanoic acid, in the end, you have 987 remaining, and these number here of hydrogen and ethanoic ions produce. So for every one of this all, you have a low concentration of that. Acid must be very weak. If an acid is weak, therefore, you won't have so many ions inside. And what do you expect of its conductivity? Would it be high? Mind you, the ions are responsible for conduction. It's going to be poor conductivity. That's why in this reaction here, we have a conductometer here. There's a bulb here. You can see it lights so brightly here. See that? And this one here can see how dull it is, okay? That means that acetic acid there conducts electricity very poorly. So we are saying is that compare hydrochloric acid with acetic acid. We say hydrochloric acid is a strong acid and acetic acid is a weak acid. So this is a little quiz I give my students here. What are the differences between 1 mole per liter acetic acid or ethanoic acid or vinegar acid, sure you call, and 0.1 mole per liter HCl. What are some of the differences? First of all, in terms of molarity, in terms of its concentration, acetic acid here will be 10 times more concentrated than HCl. Even though this guy is 10 times as concentrated as HCl, it still remains a weak acid because it is poorly ionized. All right? What else you say? And if you put a pH meter into both of them, pH is a measure of the H plus ion concentration in a solution, you're going to find you have a higher H concentration here and a lower pH. The higher the H concentration, I'll do that later on, the lower is the pH. Hydrochloric acid at all times will have a lower pH than a weak acid such as acetic acid. So these are the three differences that you have there. Conjugate base strength. All right, let's watch this now. Remember the last time we talked about conjugate base? If this is the acid, when it ionizes, what's left of it is its conjugate base. All right? This is the hydrogen that leaves, and therefore the Cl ion here is a conjugate base. Why the conjugate base of a strong acid is weak? Look, it's acting as a base. In the reverse reaction now, it should be something like this. Let's say it's like this, okay? It's going like this, and it's going like this. In the forward reaction, this is what is happening here. Water is acting as a base. It accepts the hydrogen and becomes hydronium ion. In the reverse reaction, now look what happens. This guy is trying to push its proton onto this. But it doesn't want it. It's very reluctant to take that proton. Very reluctant to take on that proton. That is why now it is 100% ionized. And we'll say the fact that this doesn't want to take up that hydrogen there is a weak base. So base is something that's supposed to accept a proton, right? So the fact that it's not doing that willingly, we'll call that a weak base. That is the discussion here about what I just explained here. It's reluctant to take the hydrogen from the hydronium ion, and we call that a weak base. Look what happens here now. This is now representing the partial ionization of acetic acid. This is the hydrogen that breaks off because of that polar OH bond here. That's why anytime I do this acid here, I always highlight the hydrogen that is ionizable. These will stay all by themselves, and that will be your acetate ion there, and this is a conjugate base. Watch this. In the forward reaction, water is unwilling to take this hydrogen here. Or you can say this guy is unwilling to produce the hydrogen, okay? In the reverse reaction now, where this guy is going to try to donate the hydrogen to that one, right? That reaction going back that side now. The ethanoic ion is willing to accept the H plus ion. That's why it is now going to go and form acetic acid here, okay? Where this is 98.7% in solution. This is what you're going to have. So because this is willing to accept that proton, we say it is a strong base. So 2 points. A strong acid has a weak conjugate base, and a weak acid has a strong conjugate base. What we talk about now, we're going to compare a strong acid with a weak acid. So strong acid, weak acid. In terms of electrical conductivity, because of the high degree of ionization of strong acids, there will be lots of ions in the solution there to conduct the electricity, as opposed to this one here, where there are few ions to conduct electricity. So you have high conductivity here and low conductivity here. Degree of ionization, same argument, I said that already. High degree of ionization, low degree of ionization. pH of this is going to be low because it's negative log of the hydrogen ion concentration. This is going to be higher. Conjugate base, weak. Conjugate base, strong. This table here summarizes most of what we've spoken about already. Strong base versus weak base. Something similar to that is happening here. When you have a strong base, initially, you have 0 of these, 0 of these. But when it does ionize, see, you don't have any of these remain because it's completely ionized. So you have exactly 1 mole per liter here and 1 per liter here. We say this is a strong base, complete ionization. There are others which only partially ionize, like ammonia, for example. We react with water, give ammonium ions and OH ions there. Okay, so only a small concentration of that you have in weak bases. Again, you're seeing this here indicating to you partial ionization. Acidic hydrogen in acids. When you look at the formula of an acid, you can identify the acidic hydrogen. This one here will be the acidic hydrogen, this will be acidic hydrogen, and this will be acidic hydrogen here. Here you see each of these here is having 1 mole of hydrogen per mole of acid. And because of that, we call these monoprotic acid. So if you look at an acid and you only seen 1 hydrogen ion inside its molecule, we say that that is a monoprotic acid. Okay, so these are capable of ionizing to produce 1 mole of H plus per mole of acid. Even this is a weak acid, it can produce an entire mole of that, because what should happen? If you try to neutralize that acid with bases, I'll just introduce this quickly. It reacts with this guy here, the base will produce this, and it forms water, okay? This will form water here, the H and the OH really are water reacting. So when you start removing these guys, it shifts the equilibrium this direction to produce more H plus, and you have more of these guys to react with them. They continue to give water. Eventually, all of this will shift in that direction, and it'll be completely neutralized. So never mind this weak acid. If you have 1 mole of acetic acid and say 1 mole of sodium hydroxide, which has 1 mole of OH, it will eventually neutralize this whole thing, as I have explained that to you. So note that. Diprotic acid, this is H2SO4. You can see there 2 H's there. So diprotic acid is capable of producing 2 moles of H plus per mole of acid, okay? One thing to know, however, is that these acids ionize sequentially. First of all, this H2SO4 ionizes for us to give 1 mole of hydrogen and 1 mole of hydrogen sulfate ions. Then this one now will ionize further to give you another mole here, and then you get a mole of sulfate ion here. So note that, eventually you get 2 moles. But it ionizes in a sequential way, where first mole is produced, then after that, if conditions are right, then the other mole gets produced there. Okay, triprotic acid now. These have like phosphoric acid. You have 3 moles of hydrogen there. And again, this is a weak acid. That's why we're showing you these double arrows there. It produces that. It's left with that. Okay. Note how you have 1 negative charge because 1 hydrogen is lost there. This here produces another mole here. 1 mole is left there now. This negative charge increases by 1. And finally, that gives you this one. So you have all 3 here eventually, but that it doesn't happen so easily. In fact, if you were to put phosphoric acid in water, you will never find these ions there. You'll only find a bit of that and a bit of that. It's a very, very weak acid. But again, if I have 3 moles of NaOH and I drop it in 1 mole of phosphoric acid, because you're having 3 moles of OH ions here, eventually all 3 of these get neutralized and you form sodium phosphate. Okay? So that is what I want you to know. I'm saying the ionized sequentially. So look at the point I'm making here about this acid, like sulfuric acid, for example. If I drop in 1 mole of sodium hydroxide in sulfuric acid, because here you're having only 1 OH here, and that will be capable of neutralizing 1 mole of H plus ions. So you get water there, but 1 mole of hydrogen is still left in the salt here. This salt is said to be acidic because you put it in water, it can ionize, to produce this hydrogen can come out of solution there and make the solution become acidic, okay? This guy here now ionizes to give this one here. See? But this one here now still has that H plus locked up inside that can partially ionize. Okay, it partially ionizes. You see double arrow there? It's only 20% ionized. The second hydrogen is only 20% ionized. First hydrogen is 100%. Second hydrogen for sulfuric acid is only 20. But put another mole of sodium hydroxide inside, it neutralizes it completely, okay? You get salt and water there. So the summary equation will be what? 1 mole of this, because a diprotic acid will take 2 moles of sodium hydroxide and for complete ionization. Hydroxide ions and bases, again, what I'm going to say, I don't know if this is correct, but why don't you be brave enough to say that this guy is a monoprotic base because he has 1 OH, and any monoprotic acid is capable of neutralizing it, right? We call it a monoprotic base. It has 1 OH, okay? Because they're capable of neutralizing 1 mole of a monoprotic acid. Next, another example. MgOH has a 2 there. We call that a diprotic base because it's capable of neutralizing 2 moles of a monoprotic acid. So this is when you balance the equation there because of that 2 there, right? You have to put 2 HNO3 because this has only 1 mole of hydrogen. So you need 2 moles of hydrogen to neutralize 1 mole of MgOH. And now you can have another diprotic base here. Will neutralize 1 mole of a diprotic acid, right? That's why you don't put any coefficients there. So 1 mole to 1 mole and complete ionization there. And here you have some nice questions there for you to practice your skills based on what you've learned. These are repeated in the your solutions manual. The answers are there. Okay, explanation of the answers are there. Now we talk about acid-base neutralization. We have alluded to that just now. So acidity is caused by the ability of the molecules to produce H+. Basicity is the ability to produce OH ions. Okay, so an acid-base reaction really involves the reaction between OH ions and H+ ions to form water. So this is a general equation here for a neutralization reaction, where you have an acid reacting with a base to give you salt and water. Both of these here are neutral compounds, right? That is why we call that a neutralization reaction. So the reaction between HCl and sodium hydroxide is used to depict that. In this case, you get in sodium chloride and H2O. Now make a point here for you to note that even though in all neutralization reaction you're going to get salt and water, what happens sometimes is that depending on if the acid is strong or weak, okay, the salt that is formed sometimes undergoes something called hydrolysis. Okay? It will react with water, disrupting its H and OH ion concentrations. You know, water has an equal concentration of H and OH. That's why it's neutral. Just note that. But generally speaking, a neutralization happens when an acid reacts with a base to produce salt and water. Ionic equation, again, just like we did in one of our previous lessons, you break the acid down into these ions here. These are the ions. Sodium hydroxide give you these here. And this is what you have. Take out the spectator ions goes, spectator ion goes. What you're left with is this one here, and this one here, and that forms water. So this is your net ionic equation here. That's what you get there. You get a little bit of heat, called heat of neutralization. That's your enthalpy change there. You in grade 12 chemistry will talk about enthalpy of neutralization. That is happening when these OH and H react together to form a molecular compound here, and energy is being produced. All right, balancing acid-base neutralization equations. All right, so watch this. We alluded to this already. This has what? 2H there. and you have only one there. So what do you think is the obvious thing to do? You need two moles of these, then you're going to put a 2 in front there, okay? So note that. It's a guide towards balancing acid-base neutralization reaction. You watch with the OH, number of OHs present, compare that with the number of H's present there, and you can know what to do. You've seen 2 H's there. This has only 1 H. Obvious thing is to put 2 in front there, and you balance that equation. Okay? Now here, you have a diprotic base, 2 OHs, and you're balancing with this. Here, this one has 1 only, so you need to put a coefficient of 2 there to do that, and that's this there. Okay, and here you have some nice equation there for you to balance, complete and balance these more, and that's it.